Okay, so take a look at this little um, chemical journey here. See if we can fill in the things in the boxes. Okay, so SOCl2 is thionyl chloride. What sort of functional group does that make? Yep. So, well, the only functional group that we have that can react is the carboxylic acid, so the rest of the molecules can stay the same. And then acid, in this case, acid chloride, just has a chlorine right there instead of the OH. Yes.
Fill plus SO2 and plus HCl, right?
Sure, but I'm just looking for the organic products, yeah. Okay. So we're in two different reactions with this. If we add methanol, which is an alcohol, to our acid chloride, what sort of functional group do we get from that? Ester? I hear people saying ester. Yeah. Okay, so an ester has an oxygen here. And then what is going to be the group that's on the oxygen? Yeah, the methyl. So you could either draw that, just a methyl group as a line, or just to keep it consistent with what I've drawn here. Okay, so We go in this direction, we take our acid halide, react it with this carboxylic acid salt, so I've written it ONA, but you could also write it like minus Na plus. And that's a carboxylate salt. So what functional group is this gonna make? Acid. Anhydride, yeah. Okay, so we'll start with our like main starting material. So the anhydride is gonna start like that. And has that structure where you have two carbonyls next to the oxygen. So this first carbonyl, of course, is from this reactant, and the other carbonyl is going to be this carbonyl. So what's, well, we've got an oxygen here, that's this oxygen. And then what's on the other side of the carbonyl? Well, 10 over. How's that color? So in red, we have the part from the acid halide. In blue is the benzoate. And then in black here, that's the bond that's actually formed between the two. So the oxygen from the anhydride comes from here. And I mean, there's not an oxygen here, so one thing. Okay, so this is going to pick up where we left off. Questions on this? Okay, 4 methods for making carboxylic acids. This is good because it's a really sort of parent functional group. It's nice that we have several ways to make it. The first is the ozonolysis of alkynes. But I think we talked about ozonolysis of alkenes just briefly. But we're going to do this again just with alkynes. So this is all kinds of fun. So you take an alkyne with, in this case, we'll have 2 different. Thank you. It's a really old joke, but I figured you guys probably had. Okay, we take an alkyne with 2 different R groups. We use O3 ozone And then aqueous workup. And that's gonna do sort of the same thing that the ozonolysis of alkenes did. And that is split the multiple bond down the middle. And then when we did alkenes, it oxidized it to a ketone or an aldehyde. But this carbon has got 3 bonds other than its R group. And so that's going to go to a carboxylic acid. So we end up with this. So instead of the space in the middle getting filled with ketone, it gets filled with 2 carboxylic acids between 2. So this method, we kind of talked about something similar to it when we did aldehyde and ketone chemistry. In addition, we also talked about oxidation of alcohols for doing aldehydes and ketones. And this sort of stuff actually works also for carboxylic acids, just with slightly different conditions. So we have if we have a secondary or tertiary alcohol, got too much stuff on this carbon. So like if we had this kind of thing going on, there's too much stuff on that carbon to oxidize it to a carboxylic acid. So we're going to need a primary alcohol. And now we treat it with the same reagents that we used in the last chapter. So we can use H2CrO4 or KMN. It's like it's like chemistry. Okay, we use one of these 2 oxidizing agents. And we get our carboxylic acid. Also in the last chapter, we talked about like PCC and DMP, or, all of those different things. Those are not adequate. So if you were to treat that primary alcohol with PCC, you would just get an aldehyde and not carboxylic acid. So you need a stronger oxidizing agent like those 2. Okay, another annoying reaction, at least in synthetic chemistry, that is hydrolysis of nitriles. So if we have some sort of nitrile and we heat it with some acid. Now, this is sort of, I'm implying that this is a bad reaction because a lot of times it'll happen when you don't want it to. But the saving grace here is that it requires some heat. So it's not like you can have a nitrile sitting in a flask and you get a drop of acid in it and it decomposes. But you have to heat this reaction to get it to work. Gives you carboxylic acid. I guess I should say that just H plus itself is not adequate. You actually need some water. Otherwise, where your oxygen is gonna come from. But in this case, and really all throughout this course, when I say H plus, what I really mean is water with acid or hydronium ion, any of the. Okay, the final method is totally the coolest. And that is the carboxylation of Grignard reagents. So if we have a Grignard reagent, our magnesium bromide, usually what we would say to do first, like, what kind of thing do you add to a Grignard reagent? A ketone, right? Or something like that. And so a ketone is just like that. But what if instead of having two R groups on the ketone, we instead make it a ketone on both sides? What's that? Everybody knows what this is. Okay, we're not continuing until you told me what the name of that compound is. Carbon dioxide, CO2. So why don't we use CO2 as an electrophile in the Grignard reaction? Okay, so what this does is it's going to form a carboxylic acid, but look at the structure of a carboxylic acid. It's got an R group, a hydrogen, and in the middle, there's your CO2 molecule. So, actually, yeah, let's show it step. So, do CO2 first, and so that gives us right, our CO2 just attaches to the R group. And then when we add water or a little bit of acid or something like that, we get our carboxylic acid. So one thing to notice about this is that you're always going to add one carbon to the molecule. I mean, we're adding CO2, so hopefully that would be obvious, but what you got to make sure of is that when you're doing an example reaction, so let's take this alkyl halide for our Grignard. This is a C3 molecule, so it's got 3 carbons. So we do magnesium, make our Grignard reagent, GBr. This is also a C3 molecule. But as soon as we add carbon dioxide and do this reaction, our MGBr to our carboxylic acid, okay, so we get that, which is now 1, 2, 3, 4. This is now a C4 molecule. Not a molecule of C4. That's a different type. Okay, but
What's that?
what?
I mean,
Like the explosive C4?
I know, like, how was that made? Like, that's what's been interesting to me, how it's like sticky, you know? Like,
That's because, so the main explosive that's in C4 is not, it's just like powder or something. And they just suspend it in plastic,
oh,
hence
okay.
why it's called plastic. Well, she's listening outside. Okay, so awesome reaction. And by the way, really fun. We're not gonna do it sadly, but this is something that the next group is gonna get to do it, sorry. And that is you make your drinking reagent, which, you have to sort of be really careful and exclude water and everything. Then you get a beaker of dry ice, solid CO2, you just dump your reaction into it. And it adds the CO2 group and then the water that's in the air, hydrolyzes it. Sorry, I'm a nerd, but it's really. Okay.
Yes.
No time. And also the last lab we're gonna do is also pretty cool as well, so. You can look it up, just look up, bring your CO2 or something.
But you don't do it at home.
Yes, do He'll give you more money back.
Thank you. Okay. Okay, so we looked at synthesis, and those are our 4 methods for making carboxylic acids. Don't get too excited about this one because a lot of times you're gonna need to not add a carbon and you're gonna have to do something like that. Anyway. Okay, reduction of carboxylic acids. This generally is pretty easy to do, but you have to determine in advance if you want to go to an alcohol or an aldehyde. So actually, let me do that first. Okay, so here's our carboxylic acid, aldehyde, and alcohol. So these are all related in that we have an oxygen atom. Well, what I want to do is look at the central carbon and say, okay, how many bonds to what do we have? So let's do bonds to oxygen and hydrogen. Those are the 2 most important. Okay, so in a carboxylic acid, we've got 1, 2, 3 bonds to oxygen and no bonds to hydrogen. Assuming that R is a carbon atom, we can assume that. In the aldehyde, we've got 2 bonds to oxygen and 1 bond to hydrogen. And in the alcohol, we've got 1 bond to oxygen and 2 bonds to hydrogen. Okay, so this sort of stuff here we refer to as the oxidation state of the central carbon. Now you're probably thinking, okay, in general chemistry, oxidation state is like if you have a metal and it like has maybe it's like an salt and you look at the charges and stuff. So this is not really the same thing, but it's kind of going on the same idea where we're looking at the types of different things that the carbon atom is bonded to. Kind of doesn't mean too much, but so this over here is less oxidized, more reduced. And over here, this is more oxidized, less reduced. I just want to make sure that everybody sort of is on the same page with the words that I use for oxidation and reduction in carbonyl-chemistry, as opposed to like general chemistry. Okay, so reduction. So how do we go this way? Increased reduction going from carboxylic acid to aldehyde to alcohol. So going all the way to the alcohol is the easiest because we can use a very strong reagent and just push it all the way to the right. And we use for that lithium aluminum hydride. That's going to give you the alcohol. So we can't use NaBH4 here. Not strong enough. And additionally, you cannot stop at the aldehyde. So this has to go all the way to the alcohol. For aldehydes, we can't just blast it with lithium aluminum hydride. So we need sort of a milder reagent, and that's going to require some more nuanced chemicals. First is TMS chloride, which is trimethylsilyl fluoride. So that's silicon atom with 3 methyl groups and fluorine. We also need dimol H, diisobutyl aluminum hydride. So there's our aluminum hydride part, and it's got 2 isobutyl groups, which look like that. And that gets us to aldehyde. So that's a lot of, seems like a lot of work. It's actually a pretty common reaction to do in research chemistry. Oh. There. OH. Sorry. As your sodium benzoate. Good, yeah. Okay. So esters are, I don't want to say the most important or the most useful of all of the functional groups we're going to talk about, but they're used in a lot of like not obvious applications. A lot of them are flavors and perfumes. They're pretty stable compounds, so they don't react with a lot of different things. In fact, really most of what we're going to talk about is there in terms of reactions is them just hydrolyzing to the back to the acid.
So it's kind of like what happens in
Yes. Yeah, the second synthesis reaction is going to be what we do in lab. So, yes. Okay, so synthesis of esters. The first method is by SN2 reaction. Interestingly, so we'll start with carboxylic acid, which we pretty much always have to do. And if we treat a carboxylic acid with a base, like sodium hydroxide, we're just going to deprotonate the acid and make the carboxylate salt that we saw this morning. And now we have a relatively good nucleophile. So we can take an alkyl halide or something like that. Draw this arrow, because I'm about to draw the actual arrows. And we just do an SN2 reaction at whatever this R group is, carbon atom of some kind. So we just do an SN2 reaction, get rid of our halide. And now we've got an ester with our OR. And then salts. So that's a simple, really inorganic 1 reaction because it's an SN2. But of course, you have to pay attention to the alkyl halide that you're using. So that needs to be a primary or secondary alkyl halide, preferably a primary, because if it's too sterically hindered, so if you've got that, that's not going to work because there's no room in here for your nucleophile to get in. Okay, here's the Fischer esterification. This could be on the left, but is there anything? Actually, kind of sort of that. Okay, so we take carboxylic acid, shocker, we're starting with the carboxylic acid. And we react it with an alcohol. We need some catalytic acid, and this is an equilibrium process. And from that, we get our ester, which is a combination of our original carboxylic acid, R group, and the organic group that was on the alcohol. And as a side product here, we get water because our carboxylic acid has lost the hydrogen. It's been replaced with the R group. And then, well, the R group just gets stuck on. And there's the OH, so we can write water. It's HOH. So there's the Fischer esterification. Where there's restrictions on R prime here, restrictions on one of the substrates for the SN2 reaction. That's not really the case with Fischer esterification. feel like there's always an exception to the rule, but not a really obvious exception to this one. So we've got an equilibrium arrow here. Equilibrium process. So we're going to use Le Chatelier's principle to control whether we get a lot of product or not a lot of product. And for this particular reaction, the reverse also has a name. And that is ester hydrolysis, because we are reacting an ester with water, that way to form a carboxylic acid and an alcohol. The final way we already talked about when we did acid chlorides. And that is to take your acid chloride, react it with an alcohol. This is the methanol reaction we did at the beginning. And that you get this. Okay, reactions of esters. The first is ester hydrolysis, and so that's just the reverse of the Fischer esterification. This process uses acid, but esters can also break down in the presence of a base. And that's called saponification. Saponification, the SAP part of saponification is from the word soap, because this is how you make soap. Whoa! So you take an ester like the triglyceride or some sort of fat or something like that. You treat it with sodium hydroxide. If R is a long chain, imagine just a straight chain hydrocarbon going like all the way up to here or so. You've got this long alkyl chain and then a really polar functional group at the end of it. that's soap. Sodium soaps are usually solid, potassium soaps usually liquid. This is not soap, sadly. And then, of course, you can take this, treat it with acid to get your carboxylic acid back. Almost done, sorry, one more. Okay, aminolysis. We're going to, right, add an amine to our ester. Ester, and in this case, I'm just going to use ammonia. This is a pretty slow process, and so this is not a particularly synthetically useful reaction. Again, this tends to be a problem reaction. If you're trying to do some chemistry with ammonia or some sort of nitrogen compound, you have an ester, sometimes this can create a little bit of side products. And you get an amide. And the other R group comes off as an O. Questions on esters? That's not the end totally of esters, but we're almost done. Right.